Welcome back. This is a continuation of my previous video on finding an equivalent resistor. I hope you had the chance to check it out. If not, you can find the link above. In this video, we'll dive into a few more techniques for finding the equivalent resistor. We'll begin with this example, where we need to find the equivalent resistor between points A and B. This will also help us recap some of the methods we discussed in the last session. At first glance, it may not be obvious that this setup closely resembles a Wheatstone bridge. However, I suggest you take note of this specific arrangement of resistors, as it can be redrawn to represent the classic Wheatstone bridge that we're familiar with. Now, let's apply the Wheatstone bridge condition to see if any current flows through the resistor R2. In this case, the resistor ratios on either side of the bridge are equal, meaning the voltage at node 3 is the same as at node 2. With no voltage difference across the resistor, no current flows through it. As a result, we can either connect the two nodes directly, or remove the resistor entirely, leaving the nodes open, without affecting the circuit's functionality, as shown in the diagram. At this point, we can move on to simplify the circuit by combining the resistors in series and using the formula for parallel resistors to further reduce the network. Finally, we can calculate the equivalent resistance between points A and B, which comes out to be 100 ohms. Let's move on to the next example, where we need to find the equivalent resistance between points A and B. You'll notice that the symmetry in this case is along a line perpendicular to the two nodes, between which we're calculating the equivalent resistance. This is a different setup compared to the examples we discussed in the previous video. In this case, the line of symmetry passes through a resistor, allowing us to split it into two halves, as resistors in series can be combined by simply adding their values. To do this symmetry, the voltage at node 1 is equal to the voltage at node 4. But how is this possible? Let's examine the two sets of resistors on either side of the line of symmetry. The resistor configuration within both rectangles is identical, and these sets are connected to the main circuit at nodes A, 1, and B. We can replace the resistors inside these two rectangles with the resistor configuration shown here, without changing the characteristics of the circuit. Thanks to the symmetry, resistor R sub P is identical on both sides, while R sub S is common to both. If you look closely at this arrangement, you'll notice that it follows the classic setup of a Wheatstone bridge. In a Wheatstone bridge configuration, when the resistor ratios are equal, as they are in this setup, the voltage difference across R sub S becomes 0. This means the voltage at node 1 is the same as at node 4. I hope this explanation is clear, but if not, feel free to share your thoughts in the comments. Now that we've understood that, let's return to the original circuit. Now we have two options: either leave the two nodes open as they are, or combine them since they share the same voltage. The decision depends on which approach simplifies the process of finding the equivalent resistance. In this case, it's easier to combine the two nodes to speed up the calculation. You might also encounter situations where there's a resistor along the line of symmetry. In such cases, you can remove the resistor, as the voltage drop across it is 0, and either combine the nodes, or leave them separated, depending on which approach simplifies the process, and reduces the steps needed to find the equivalent resistance. Alright, let's combine nodes 1 and 4. Now, we're left with two resistors in parallel. We can use the formula for parallel resistors to find the equivalent resistance, and replace the two parallel resistors with a single resistor. These two resistors are in series, so we can simply add their values to find the equivalent resistance. Alright, we're now left with these two sets of parallel resistors. Just like before, we can find the equivalent resistance for each set. Now we have two resistors in series. The final step is to combine them by adding their values, giving us the equivalent resistance between points A and B. Hope that explanation was clear. Before we proceed with the video, I would greatly appreciate it if you could kindly give it a thumbs up, subscribe to my channel, and activate the notification bell. Your support means a lot. Thank you. Now, let's get back to the video. Let's dive into this example, where resistors are arranged in a 3D structure, forming the edges of a cube. Each resistor has the same resistance value, creating a symmetrical setup across all connections. Our objective is to determine the equivalent resistance between two pairs of nodes, first, between nodes A and B, and then between nodes A and C. To solve this, we'll leverage the symmetry within the cube. Symmetry allows us to simplify the analysis, as it ensures that the current splits evenly along identical paths. This setup requires considering the paths through which current can travel between the specified nodes, and identifying which resistors are in parallel or series configurations relative to each path. To better understand the series and parallel relationships between the resistors, and to identify equipotential nodes, we'll redraw the circuit on a 2D plane. This layout will help us more easily spot which resistors are in series or parallel and better observe any symmetry within the circuit. Let's start by calculating the equivalent resistance between nodes A and C. If you look closely, you'll notice that the circuit is symmetrical not only between nodes A and C, but also between nodes 4 and 5. We can use this symmetry to simplify the circuit, reducing it step by step to find the equivalent resistance. In the previous example, we discussed that resistors along the line of symmetry, which is perpendicular to the axis, between the two nodes where we need to find the equivalent resistance, can be removed. Here, there are two such resistors we can remove. However, we'll set these aside for now, and focus on the symmetry between nodes A and C. In this case, nodes 4 and 5, as well as nodes 2 and 3, share the same potential. This means, we can combine each of these pairs into a single node. By doing so, we can replace each pair of parallel resistors with their equivalent resistance, further simplifying the circuit. These two pairs of resistors are in series, so we can combine each pair by simply adding their resistor values to find the total resistance for each series pair. I'm sure you've recognized this configuration as a Wheatstone bridge. In this setup, the voltage across the resistor on the vertical line of symmetry is 0, which means we can either remove this resistor or connect the two nodes directly with a conductor. As we discussed earlier, any resistor along a line of symmetry perpendicular to the axis between the nodes for which we're finding the equivalent resistance can be removed or have the nodes directly connected. While we could have made this simplification from the beginning, I wanted to demonstrate the reasoning behind it, rather than just following instructions blindly. I hope this approach helps you understand more clearly why this simplification is possible. We'll remove this resistor and proceed by simplifying the circuit, replacing the remaining series and parallel resistors with their equivalent resistances. Step by step, we can work through each simplification to find the equivalent resistance between nodes A and C. I hope that explanation was clear. If anything was unclear, please feel free to share your questions in the comments. Next, we'll proceed to find the equivalent resistance between nodes A and B. Unlike determining the equivalent resistance between nodes A and C, finding the equivalent resistance between nodes A and B shows symmetry along only a single axis, the axis directly between nodes A and B. To determine the equipotential nodes, let's apply the technique from the previous video. Starting from one end, say node A, we'll move along identical branches, taking the shortest paths to reach the other end, node B. No matter which path you take, you'll encounter 3 resistors and 2 nodes. For instance, moving from A to B, you could begin at A, and reach one of nodes 1, 4, or 5. Let's say you pick node 4, from there, you can proceed to either node 2 or C. Or if you proceed from node 1, you can pass through nodes 2 or 3 to get to B. What does this tell us? It indicates that nodes 1, 4, and 5 are at the same potential, just as nodes 2, 3, and C are. This equality of potential is crucial for simplifying our circuit analysis. To make these equipotential nodes easier to identify, let's mark nodes with the same potential, in one color. As it stands, identifying series and parallel resistors here can be challenging, so let's redraw the circuit for a clearer view. First, identify the two nodes, between which we're finding the equivalent resistance. Next, draw lines marking the equipotential nodes, and then place each resistor carefully between these lines, one at a time. You'll want to do this patiently, ensuring no resistor is left out. Now that we've placed resistors between equipotential nodes, it's easy to spot the parallel connections. Since all these parallel resistors share the same value, we can find their equivalent resistance by simply dividing the value of a single resistor by the total number of resistors in parallel. With this done, we're left with just one final step, finding the equivalent resistance of the remaining three resistors in series. For resistors in series, we simply add their values to get the total resistance. And with that, we can determine the equivalent resistance between nodes A and B. That brings us to the end of this video. Thank you for sticking with me until the end. I hope it helped you understand how to use symmetry to simplify circuit diagrams and find the equivalent resistance. If you haven't subscribed yet, please consider doing so. It would mean a lot to me. And if you found this video helpful, give it a thumbs up, and share it with your friends. Until next time, stay safe, and goodbye.